All right, how's it going? Great. You survived PA3. Hope so. If you're here, you survived. So the bad news is that more than a quarter of the students in this class have not turned in PA3. And if that's the case, you've already gotten an email from me this morning on Canvas saying I'm missing your PA3. So if you have not turned in PA3, please either turn it in or come and talk to me today, and let's get your repo in shape. Okay, I have office hours at 11:50 after the next section. I have office hours at 2 o'clock in my office. Come by if you don't know how to get your repo set up, right? And let's figure that out. If you're completely lost on PA3, let's talk about it today, okay? And let's get you on track, because we're just going to keep building on the stuff we've been doing. So I will get stuff graded this weekend. Monday is a holiday, right? So no class Monday, but I'll get stuff posted by probably this weekend, grade-wise and such. So burning questions, issues, last thoughts on PA3? Things you just couldn't figure out? Yeah.
So I did have this issue with background.
Okay.
I talked about on the Discord server last night, and I think they eventually got it figured out. But it was one of those errors about the jump based
Right.
initialized value. And so it was in a function that was just, its function was to trim a new line character off.
Okay.
And so it took in string as an argument. And that's where it was complaining. So apparently it was tracking the variable being passed in, that it was uninitialized,
okay.
in, but then also immediately before I called that function, I also called fgets to load stuff into the string.
Okay.
So it seemed to me like there shouldn't be any way that it should be kind of initialized.
Yeah.
It was weird.
If you can show me, if you still have code that throws that error, if you can show that to me, it would be good to run down. Valgrind is really powerful. Sometimes it's a little mysterious where it's getting its idea that there's something wrong from. But yeah, I mean, it could be something like an edge case, like the first time that you call it, or something like that.
I ended up just initializing it.
Okay. So fgets is not guaranteed to change the value of that string, right? If you had hit Control V, then that string would be uninitialized. I don't think it's noticing that. Like a Java compiler will actually notice that there's a possibility the string was not initialized. I don't think Valgrind is looking at the code, but could be something along those lines. But yeah, initializing it takes care of it. That's a good fix. And so this was, a big assignment, right? Because you were using all of the pieces from PA2 for your list class, your list structure, and then using that as a building block for this new structure, which was the hash, and then putting it inside a main program and interacting with file I/O to read the database. So lots of parts and pieces to this, right? And so it's definitely, good work to get most any of it done and working. And if it's not 100% perfect, that's not a huge deal. But I'll go through it and I'll post comments and we can talk about it. By the way, just for the record, the helpful experts at Chegg weren't even able to do this. This was up almost 2 weeks ago. Somebody posted the question, and it still hasn't been answered. So yeah, so kudos for getting it done. All right, so ODPs are back. I have posted an ODP. Yes?
Does Chegg pay anybody that puts an answer? Or?
You have to go through an approval process, and I don't know how stringent it is because I haven't done that. there was some talk about doing that and stinging people, but that's not really my interest.
Okay.
But they claim that they vet their experts and, you know, randomly test their qualifications and stuff like this. I don't know if it's true or not.
Is there a reason we don't have access to the reading file for the other people?
Oh, my bad. Thank you. I knew I was forgetting something.
Well, I guess we're gonna have to extend the due date.
I already did. It's not due till Sunday.
Wait, this is an NODP.
It's a TDP. Don't remember.
211.
211. All right. So yeah, so this isn't due until Sunday morning. Well, that was pointless because it's going to say see the readme. So /temp is a directory that anybody can write to or read from. Yeah, it's a general temporary area. So if you have a program that needs to make a temporary file and you don't want to clutter up the runner's directory, you can put it in /temp. And so you'll see lots of things in there. Some screenshots, those are interesting. I'm not on the server, am I? So this is all, you know, stuff that belongs to different people.
So do all servers have a /temp?
So all Linux servers have a /temp area, and I think it's almost always supposed to be readable and writable for everyone.
Is it, like, can you make a bash script in there that's just like
Yeah,
rm star?
yeah.
And it'll just rm star everything?
Well, rm star everything that's not protected from deletion.
Oh.
You just need over something.
And most files are protected, but you know, if there's a file that's writable by the world or by the group that you happen to belong to, then you could go ahead and modify it or delete it. So like the database is readable by everybody, but if you try to delete it, it won't. It'll give you a permission error. And that's almost always available on Linux systems because, you know, sometimes programs need temporary errors. But it's also temporary, so on some systems, every time it boots, it will clear out the contents of that directory so that it's not a permanent, right? And we haven't rebooted in a few months, so it's just growing. So you don't want to count on something there for long-term storage. It's really while the program's running mostly. But I throw the ODP stuff in there.
It's just easy as kid said.
All right, so ODP 211, you're building a small tree containing 3 nodes. We're going to talk about this in detail today. This is not the same tree structure you're going to use for PA4, okay? This is a tree of integer nodes. So I'm defining a structure T node that's a tree node that contains 3 pieces: data, a pointer to the left, and a pointer to the right. So it's like a list with 1 extra pointer. And you're trying to make a function called small. It takes in 3 integers and it builds a tree out of them. And then it returns the root of that tree, which again is a pointer to a struct T node. So if I call small with 3 arguments, so if I say struct T node star R equals small 10, 20, 30. Right, I should treat that first number as the root value, the second one is the left, the third is the right. So this should construct in memory a tree that looks like this. And then it should return the address of that root node. So after I execute this, R would be the address of that node containing 10. And you can do this without any looping, without any if statements. It's just a bunch of, you know, hammer and nail kind of stuff. Define your struct T node. Okay, make a struct T node called root, make another one called left, make another one called right. Okay, and you got a few ways to do this. I could say struct T node root equals malloc size of struct T node. Okay, now root is a pointer to a struct T node, that's what I want, and I've allocated space for it. Do the same thing for a node called left, do the same thing for a node called right. And now just cobble them together, right? So root data equals 10 or whatever that first argument is, which is called root, so don't call your struct T node root, but you know, give it that first value. Root left equals, well, whatever the address of this left node is, which I happen to call left. Root right equals right. Okay, that node's set up. Set up this node, set its data equal to 20, set left and right equal to null. Go to your node that I called right, set the data equal to 30, set the left and right equal to null, and then just return root, and you should get 10 out of 10, or 20 out of 20. So you're building these structures in memory, you're just piecing them together by hand. Okay, it's like when we built our first linked lists, just by defining nodes and stringing them together. So here we're stringing together tree nodes. Alright, so put it into the test bed, assess it. So the root should contain the value passed as the first argument, left should contain the second argument, right should contain the third, root should point to the left and right nodes, all the other nodes pointers should be null. So it's a 3-element tree. Does that make sense? Alright, do it today, but it's not due till Sunday morning. Alright, so I've posted PA4. Alright, there's a lot going on in here. There's a bunch of pages to this. But basically you're doing PA3 with a binary search tree. Okay, that's the one sentence synopsis. PA3 binary search tree instead of a hash table. So you run your program, it's going to read from database.txt, it's going to build a binary tree. So let's say you have, you know, ABC 1, 2, 3, and this is Jones. And this is J Jones, and you have XYZ 7, 8, 9, and this is Jerry Mouse. And you have, I don't know. So you're going to build a tree where the nodes contain the license plate, and then the first name and the last name. The license plate is the key. It's the thing that you're sorting on. Okay, the other information just kind of comes along for free. So if I were to add this, right, since XYZ comes alphabetically after ABC, this node would go off to the right. So this would be XYZ 7, 8, 9, and it's J Mouse. And if I have an AAA, and that's, you know, I don't know, whatever, that node would go to the left and have the first name and the last name. So this idea of a binary search tree where things that are to the left of a node are smaller, things to the right are larger. Smaller, larger means in alphabetical order based on the license plate. Okay. Okay, so you're going to make heavy use of string compare. If I string compare cat and dog, I should get something less than 0, because cat comes before dog. So take two strings, pass them to string compare. If the first one is smaller, the return will be negative. If the first one's larger, the return will be positive. If these are exactly the same string, the return will be 0.
And we assume that the license plates are going to be all capitals?
No assumptions about the license plate. Could be any characters.
So then the string compare, do you know, is it simply comparing the values of the ASCII code?
Mhm.
Okay, so then we should.
So whatever string compare uses, that's what your ordering is.
Oh, okay.
So a little a is or a little z is, a little a is bigger than a big Z. That's okay. Just use string compare.
So it's not exactly alphabetical.
It's not alphabetical.
Okay.
It's based on the results of string compare.
Right.
All right, you can run template 4 using the temp database.txt file to observe the following behaviors. Once I've actually written that, which won't happen until tomorrow. So, but I plan to have that posted sometime tomorrow. And that will, be your sample program to show you what kinds of things this should do. And again, minor variations are okay, but try to stick to this format as much as possible. Except for typos like somebody found in the last hour on my TA3. But I had already fixed that in here. All right, so you run your program exactly one way. Name of the program, which must be plate, followed by the database name. No other arguments possible, and this argument has to be given. So argc has to be exactly 2. If it's not, it's a usage error, report an error, and just return 1. If there is an argument given, it's got to be the name of a database file, so you got to try to open it. If you can't open it, that's an error, print a message, and exit. Return 1. Assuming you can open that file, start reading in data, you can assume that this data is all nice and clean, meaning it's 3 fields separated by spaces. Okay, the plate can have any information in it other than a space, same with the first and last name.
So I guess this is a question that I probably should have asked for PA3.
Okay.
The last name,
Mhm.
does it end with a new line or a space?
The last name technically ends with a character, right? But when
Right.
you read from fgets always puts that new line on the end.
Okay.
So when you're building your database from here, you want to strip that new line off. Right? Otherwise, when you print out last name, comma, first name, it's going to be last name, comma, new line, first name. So. All right, so you're going to read that database in one line at a time, just like you did for the hash, but instead of passing it to hash add, you're going to pass it to an add function that adds it to your tree. Okay, which we still need to go over the algorithm for. We still got to talk about most tree algorithms. All right, so when it reaches the end of the file, it closes that file. Now you have a big old binary tree that has all the license plate information, and in each node there's also the first and last name associated with that plate. All right, and then it's up to the user. So prompt the user for a command or a plate, and they can, again, either type in a license plate that they want to search for, or they can type one of 2 commands. Okay, one command is asterisk dump. If they type asterisk dump, then you're going to display a bunch of information about the tree. That's the main thing I'm going to use to assess how your program is running, right? Because it's going to read in everything from the file, and I'm going to want to look at your tree. And then the other thing is they can say star delete, space, put in a license plate. It should delete that from the tree. Okay, anything else that they type in, assume it's a license plate and look for that plate in the tree. All right, we will talk about deletion. We'll spend a couple of days probably going through deletion. Let me point out right now, you've got to use the deletion algorithm that we're going to go over in class. There are a lot of ways to delete things from trees. You won't get full credit unless you use the algorithm that we talk about. Okay? So we're gonna go through that in gory detail. My suggestion, don't ever look at anything else that talks about how to delete from trees and you won't get confused, okay? And if it's not clear how to do something, ask, right? Ask me, come by office, ask in class, something like that. That's the easiest way to avoid confusing algorithms, okay?
Is there a name for the algorithm you're going to teach us?
It's just one of many variations. It's not really an algorithm. It's just that there's edge cases and there's different ways you can deal with them.
Yeah.
And I really want people to just do it one particular way. Not because it's better or worse, but because unless I go in and I reverse engineer code line by line, I have to do my first order grading based on what happens when I delete something, how does the tree change, right? And so if you do it using a particular algorithm, I can predict how your tree should look after certain deletions, and I'll design test cases based on that. You may be deleting perfectly fine, but you're doing it in a different way and your tree comes out differently. And then I have to go in and reverse engineer your code and figure out if this is a valid algorithm, et cetera, et cetera. So it's partially a convenience, it's partially a chance to practice following a spec. All right, so what does your program output? Same as before. If you ask for a license plate, it should print out the following, okay? First name colon, last name colon. If you say star dump, you're going to produce the following information, and this is really critical, okay? Tree height, colon, space, followed by the height of the tree. New line, balanced, colon, either yes or no. Skip a line, LNR traversal, colon, and then show me the contents of the tree using LNR traversal. And that output should be plate, colon, name, last name, comma, first. Okay, so that's what we were doing before with dump. Skip a line, NLR traversal, same output, but it's going to be in a different order generally. Okay, skip a line, LRN traversal, show that data. Skip a line and then prompt the user again. Please, 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 please do it that way. Okay, if I get your assignment and your first thing is NLR instead of LNR, chances are I'm whipping through 45 assignments trying to grade these. Chances are I'm going to look at the output order. It's not going to be what I expected. You're going to lose points on that. Okay, and then it's going to be on you to come back and say no, this was the NLR traversal, and then I can look at it and say okay. And same thing with doing extra output, okay? Again, this is going to be a big database. These traversal outputs are going to be long. If you have this output, that output, in the middle of that you have a message saying the tree's not balanced, right? It's going to be hard for me to find it. Okay, so you're saving yourself points and you're saving yourself the trouble of coming back and arguing points if you stick to this format, okay, in this order. And don't put in extra stuff. Right, don't print out information about where you are in the tree in between each line of your LNR traversal, because they're going to make it really hard to tell if it's doing the right thing or not. So have all those debugs, take them out before you finish your submission. All right, the delete command either says success or plate not found. If you can delete, just say success. If you can't delete because the plate doesn't exist, say plate not found. And don't exit for any of these conditions. The only time you exit is when you say enter the command or the plate and the person hits Control-D in the beginning of the line. Your fget should pick that up, return null, capture that, use that to exit your program. Clear all your memory before you exit. And then you can just say goodbye if you want and return. All right, good on the basic setup. And like I say, I'll have sample code available tomorrow that you can actually run. All right, implementation. Here's what your tree node looks like. So I'm just calling it node here. Has 3 data fields, plate first and last, has a pointer to the left and the right. Same setup as with the lists inside your hash table. Plate first and last are just pointers to characters, so before you put something in there, malloc space. Okay, and then use string copy. And then left and right are just the pointers to the other And a handy type def that I'm going to use in here, you're not required to use this in your code, okay, but I'm going to use it in the rest of this description, is I'm type defing an uppercase node to be a struct node star. Because we almost always, other than when we're mallocing space, we almost always want a struct node star. Right, so I'm just going to use an uppercase node instead of typing struct node star. There's no sentinel node for search trees, for binary trees. So in your main program, when you want to declare an empty tree, it's just going to be root equals null. Okay, there's no tree init function. Just node root equals null. All right, functions. So you want to make the following functions. Height takes a root of a tree and returns an integer, which is the tree's height. Empty tree is -1, tree with just a root is 0, tree with nodes, it's the depth of the deepest node, which is the number of hops from the root to the node. Balanced takes a root of a tree and returns a 1 or a 0. 1 means it's telling you the tree is balanced, a 0 means it's saying it's not balanced. We'll talk about all the algorithms for this. Add is how you add a node to the tree. So you take in a root, plate first and last, and it will figure out where in the tree it should add that so that it's still a binary search tree. And then it returns the root of the tree. Okay, and this is absolutely critical. If you don't do this, nothing works. Okay, add has got to return a struct node star. And when you call this, you have to say something like root equals add parentheses root comma plate first last. This is critical because we don't have a sentinel node. And remember, our empty tree is null. So if I just call add and I pass it null and a plate and a first and a last name, there's no way that when I come back from that, that root in my main program is going to be anything other than what it was before, which was null. Right? The only way that root is ever going to change is if I say root equals add parentheses root first last plate and so on. Search, on the other hand, we're not changing the tree, we're just looking for a license plate. So I can call search, pass it the root of the tree, license plate. First and last name are just pointers to sufficiently large character arrays so that if search finds the plate, it will fill in the first and last name and it will return a 1. If it doesn't find the plate, it will return a 0. It doesn't change first or last. Okay, same setup as with hash find, same setup as with list find. Delete is wrong. I will have to fix that. Delete should return a node, not an int. So forget all of this. Okay, that's an important one. Delete does not return an integer. Delete will return a node. I'll update that and post it after classes. But you pass it the root of a tree, pass it the plate that you want to delete, and it should return the root of the tree after that node's been deleted. All right, 3 traversal functions, LNR, NLR, LRN. They take the root of a tree, they don't return anything, they print the contents of the tree in this given order, and they do it in the format listed up top. So plate last name, comma first, angle brackets, all that stuff. And then free takes the root of a tree and frees all the nodes, and it doesn't return anything. And that's it. No problem, right? Okay, so I have some suggestions, because this is a lot of stuff. You don't have to follow these suggestions. If you're confident you know how you want to go and proceed with this, right? Proceed how you see fit. If this looks potentially overwhelming, if you're not sure where to start, right? I have some suggestions. Okay, they're just suggestions, but if they're helpful, go for it. Step 1, build a tree by hand. Hey, guess what? This is like ODP 211. Okay, define your struct node. Okay, and malloc some nodes, set some data values to something that you like, and take the left and right fields and point them to other nodes and build yourself a tree. 3 nodes, 5 nodes, 6 nodes, whatever you like, right? Draw a tree on paper, give a name to each node, set each of those up in your code to be a struct node star or a big node. Do the mallocs, do the assignment of values, and build a tree, okay? It's cumbersome to do this, but this will help you with so much of the rest of this code. Because if you start off trying to make the add function work, that's a fairly tricky function. And you don't know if it's working unless you spend a lot of time going through GDB or you trust your traverse function. And how do you know your traverse function works? If you're not getting the right value, is it a problem with traverse or add, right? If you spend the time doing this, it's an hour at most to do this. But it gets you more familiar with the structures, and it gives you something to work with. And you can go into GDB and examine this and get some practice using GDB to examine these structures. That's going to be useful. Okay. So you know, make a more elaborate version of ODP 211 that works with these nodes instead of the T node from that ODP, and just build a little tree and make a picture of it that you can keep so you know exactly what your tree looks like. Okay, that's step 1.
I have a quick question on
Yeah.
delete. You may have said this, but what if you're deleting the root node? You need to pass the new root node back,
Yes.
but you're having returning an integer.
Anyone got an answer for that?
Well, you put up a display on the screen that said important.
Yeah.
which is returning a new-
I think I saw. I must have missed that.
Okay, no problem. Yeah, so the delete description is completely bogus on the assignment. I'm going to fix it. It should return a struct node star, okay? Exactly for that reason, because if you delete the root, right, you've got to change it. If you delete the last node, you got to return null. So you would have caught it anyway. All right. All right, so suggestion 1, make yourself a small tree to work with. Question 2, make your in-order traversal code, left node, right. Okay, it's about 4 lines of code. And you can run it on your test tree, and it should give you your nodes in sorted order, assuming you built your tree to be, you know, a binary search tree. You'll get this beautiful output from it, okay? And like I say, that should be a straightforward function to write because it's recursive, right? If the tree is null, just return. Otherwise, LNR on root arrow left, then print root arrow data, then LNR on root arrow right. And when I say print root arrow data, what I mean is print out the plate, the first name and the last name in some format that you can see all 3 fields. All right, so that's step 2, get your in-order traversal working. And then step 3, while you're here, go ahead and do your other 2 traversal codes, okay? They are exactly like LNR, except you just change where you print the data. NLR, you print it in the beginning, LRN, you print it at the end. But do that and make sure that it's giving you the right result on your test tree. Because inevitably, people just copy LNR into NLR, LRN, and they don't change it. And they have 3 in-order traversal functions, right? And it's really easy to change. Just take that line and move it somewhere else, okay? But do it up front while you're at this stage, and the only thing on your brain is I'm writing my traversal code, right? And just make sure that's right, then you never have to worry about that again. Okay, now do your search function. Okay, and we talked a little about search yesterday, right? Basically, you just search the 2 subtrees, search the root, and you're done from there. And you don't have to make a fancy main program where you're reading input and all this kind of stuff, right? Make an integer result, make some first and last character arrays, and just call your search function. Pass it the root of your tree that you already built, pass it the license plate you're searching for, first and last, save the return and result. If result is 1, say it's found, and print out the new value of first and last, otherwise say it's not found. And then do that again for some other plate, do it again for some other plate. Do it for a plate that doesn't exist, do it for a plate that's at the bottom of your tree, do it for the root, right? Exercise the heck out of your search function. And this is just copy and paste and paste and paste and edit, right? And you can totally develop and debug your search function using this. Okay, side note, this is a really good chance to get better with VI. Okay, this kind of code, well, if you do it in gedit, it's really easy to do, but don't do gedit, right? But if you do this in VI and you're going down with the arrow keys and your backspace and you're typing, this takes a lot of typing, right? If you wanted to make 10 searches, that's a lot of typing. And if you copy and paste with the mouse, you got to arrow back and change things and so on and so forth. Take it as a chance to play with VI, right? Especially if you're doing this, like, you know, over the next few days. You can copy lines of text in VI by using uppercase Y. If I say 10 uppercase Y, it will yank 10 lines of text starting with the line I'm on into what's called the yank buffer. We call it the clipboard now. And when you type a P, it will put or paste from the clipboard into your file at whatever place you're at. Okay? And you know, if I've already yanked those 4 lines and I want to make 9 copies of it, I can just keep hitting P, move down, hit P, and so on. Right? It's very fast. If I want to move across a line, I can use the arrow key to go back and forth. I can also use W and B, right? Not if I'm in insert mode, though. But if I'm not in insert mode, W will move you a word at a time, B will move you back a word. So if I want to get to where it says yet another plate and change that, right, I can just W until I get to the start of that. And once you're looking at a word you want to change, you can say CW, and that will let you replace an entire word. So what is a word? Well, there's rules for it, but if I'm sitting at the beginning of where it says yet another plate and I type CW, whatever I type will replace that particular string. Right? Really fast way to make changes. If I want to go down and go to the start of a line, I can just hit enter instead of a down arrow key. And so if I've pasted, you know, multiple copies of this and I just change this word, I can just go enter, 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 and I'll be sitting right here. Hit W a few times till I come here, say CW, put in my new word, enter, 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 hit W a few times, CW, and so on. You can get patterns and rhythms going with this that will be a lot more efficient than arrow key and backspace. And so if you're not really comfortable with VI, right, start playing with it. Take a few hours, mess around with some of this stuff. Guarantee it will save you time, right? Students come to me and they're trying to figure out a problem with their code, and the ones who are fluent in VI, they're spending all of their brain power trying to figure out what the bug is in their code. And it's a huge difference, right? Compared to trying to figure out how to get down to the right line and go out of insert mode and all this kind of stuff. So just a suggestion there, right? Side note, good chance for some VI. Okay, step 5, do your add function. Again, don't try to do fancy input. Don't bother parsing the input file. Just make some hardwired code like root equals add root new plate Mayan name, right? And that should add a node to your tree and then call your LNR function, which you already know works, and see if it added that node to the tree. It should add it so that your output is alphabetical based on license plates. So you can add 5 or 6 license plates and call LNR after each one and make sure that those are getting added. All right, and then try that same thing, but start with an empty tree. So now put away your tree that you created by hand and just initialize tree to null, or root, right? And then set root equal to add root with some plate information. The movement from an empty tree to a non-empty tree, that's a big leap, okay? So try to get that working. And that's the same trick with delete. When you delete the root node, you have an empty tree. When you add to an empty tree, you end up with a non-empty tree. So exactly the same thing. We're assigning the return value back to the root. Once your add function works, now you can ingest the database file, right? And instead of hardwiring adds, just add, you know, plate first last that you read in. You've got your code from your PA3 for reading from that file. So go ahead and use fopen gets and close to read in that file and build your big DST. Okay, probably at that point, go ahead and do your height and your balance functions. And those are a few lines of code each. and we'll go through pseudocode for those again. General note in here, inevitably some people get caught up on this max function. I talk about a max function when we write pseudocode. When we do dynamic programming, we'll talk about a max function. And it's easy to get derailed trying to figure out what is this max function, right? And there's not a built-in max function in C, and if you start looking online, you'll find all kinds of macros and extensions and special ways you can compile and libraries and things like that. Don't go down that path, okay? If you want the max of two variables, write an if statement, okay? If you want a max function, make a max function that takes two arguments and use an if statement. If you really want to be slick, make yourself a macro if you want to play around with a macro package. But be careful, because that's how I lost 2 weeks of my life. So, you know, there's an if statement for doing something based on the maximum of A and B. If A is bigger than B, do whatever you want to do if A is the max. Otherwise, do what you want to do if B is the max or if B and A are equal. All right, now you can probably go ahead and start on your main program. Right? All this stuff before is just hardwired code, just testing each segment. Once you've got all those pieces working, go ahead and put them together in the main program. So deal with the command line argument, wire up the ingestion of the database, and then go into your loop that uses fgets to get commands from the user, prompts, calls all these functions, and so on. And then step 10 is the delete function. I would leave that for last for a few reasons. One, it's the hardest function to code. Two, if you have all these other pieces working, you can use them to help you with delete. But if you're not sure that your search function works, or you're not sure that your LNR function works, and you try to run your delete code and it doesn't seem to be working correctly, right, you're not sure where the problem is. And delete's usually a lot of code, and there's a lot of detail, and there's edge cases, and it's really useful if you have all these other tools in place. If I can call search and see if it's in there, if I can call LNR and see exactly what the tree looks like, and so on. All right, so there's a suggestion, about 10 steps. Some of those are more than one thing. Some of those are fairly short. Some of those are going to be pretty long, like multiple days. Okay, you got 14 days, a little less. If you don't do any of this until Monday, you're down to 11 days, which means if you work every single day and you get exactly one of these done every single day, you've got like one room of wiggle room, 1 day of wiggle room, which is not very comfortable. So you really want to start on this as soon as possible. And, you know, if you do step 1 and you're done in a few hours, go on to step 2. Leave yourself some space, because some of these are going to take more time. And programming, as I'm sure you know, is not something you can necessarily force. Okay, it's not something that if you're behind, you can just do an extra, 12 hours tomorrow and catch up, because it's hard to program for 12 hours effectively. Right? It's just not that kind of process. There's a limit to how much you can do this, and then you have to take a break. So pace yourself, right? If you don't want to follow these, come up with some sort of plan of attack for yourself. How are we going to go about doing these? All right, and then submit it to GitLab Plate PA4. Same gig as usual. All right, clear enough? Let me talk quickly about the add function. Let me start talking about the add function, because that's going to be one of the first ones you make. We've already talked about traversal, right? Let me talk about the add function. So, and I'm just going to work with integer data, so I don't have to malloc and string copy and all that kind of stuff. Suppose we have a tree, its root is root, and we want to add a piece of data to it. Let's say our tree looks like this. Suppose I want to add a 16 to this. We don't want to change the internal structure of the tree. We don't want to start moving things around. We don't want to shift things around. We want this to be efficient. So the usual approach would be to start at the root. So let's do add 16. The usual approach would be start at the root. 16 is bigger than 10, move to the right. Smaller than 20, move to the left. Bigger than 15, move to the right. Smaller than 17, move to the left. There's nothing there. That's where the 16 goes. That's the whole algorithm. But this business of moving to the left and the right takes some work. You have to have pointers, and once we move to the left, we need to know where we moved from so that we can change that thing's left pointer. So we can do this recursively. Okay. So if root is null, make a new node with a data value of data and return it. So the edge case is if the root that you're adding to is completely empty, just make a single node containing your data and return that as the new root. Okay, if you don't do that, if your data is less than the root data, say we wanted to add a 3, right, or a 7, something less than this, then our whole approach is, let's just add it to this left subtree. So add to root left our data. And that's going to give us a new subtree over here and set root's left child to be that result. Okay, else root right equals add root right data, and then return the root. So logically, what's the argument here? If the root's empty, just make a single root, return that. Otherwise, if the data should go to the left, add it to the left subtree. Set root's left subtree to whatever the result of add is, and return the original root. Otherwise, add it to the right subtree, set root's right subtree to that new tree, and return the root.
How would duplicate values be handled?
Oh, we're going to assume no duplicates. You do have to deal with that.
Seems like there are exemptions for license plates, but
Yeah. It's a complication. It's not impossible.
I assume a lot of the times you probably just ignore duplicates.
So yeah, if we were going to deal with it, we would say ignore duplicates. Since we're reading from a database, I'll give you a database with no dupes. But I mean, you could have the same number in here twice, but it will complicate some of the other algorithms. So most of what we talk about with trees, we'll just kind of assume no dupes.
If you had to have them, how would you handle that?
There's different ways. I mean, if I wanted to put in another 16, right, I could put it here, or I could put it here.
And you just do it less than or equal or equal.
Yeah.
Alternatively, couldn't you just have another field in your structure node to count? And you just keep them as that?
If you just wanted to count, but if it was something like multiple license plates with different names or something, you might want separate nodes. So yeah, this is a pretty bare bones tree we're dealing with, but there's lots of possibilities. All right, good enough for now. I'll see you next time.